Hello, dear students. I am happy to meet you once again through this second lecture on numerical problems and solutions from the chapter EMF of the electrochemistry. Students, during this COVID-19 pandemic, I hope that you are all staying at home and stay safe. I request you to stay at home and stay safe. With this request, I would like to start my lecture. In this present lecture, I would like to discuss on the various types of problems in the present electrochemistry on the EMF of the cell. They are potential of cell, EMF of the cell, standard free energy change and equilibrium constant, calculation of pH on quinhydron electrode. And this is one of the general problem I am going to discuss. Now, I will take the problem one by one. What is the potential of cell consisting of zinc electrode dipped in 0.01 molar zinc sulfate solution at 298 Kelvin, given that standard reduction potential of zinc is equal to minus 0.763 volt. See, read this problem. What is the potential of off cell? It means that they are directly asked to calculate the potential of the off cell. Then what is the off cell here? Consisting of zinc electrode dipped in zinc sulfate solution. It means that there is only one zinc electrode that is dipped in one electrolyte called as zinc sulfate solution. So this consists of an off cell. The concentration of the zinc sulfate is given, that is 0.01 molar, and standard reduction potential of the zinc electrode is given, that is minus 0.763 volt. Okay, these are the given data present in the problem. That is standard reduction potential of the zinc, that is minus 0.763 volt. Molar concentration of Zn2 plus is 0.01 molar, and what is the potential of the off cell. So how to calculate this potential of the off cell? By using the Nernst equation. The Nernst equation for single electrode, you know that you have been derived the equation for calculation of the potential of the single electrode by using the Nernst equation. So this is the Nernst equation. In this Nernst equation, 2.303 RT by F, this R is called as Joule's constant, that is 8.314 Joule per Kelvin per mole, and this T is 298 Kelvin, you know, and F is 94,486. Calculating these constant values, which will give you 0.0591 divided by N. Then log of 1 divided by molar concentration of the ions, and the unit is volt. And you can write this equation also in this form. Instead of minus, you can also write plus if you remove this inverse. So I have to use this either of these two equations to calculate the off cell potential of the zinc. So that this equation I have to write to calculate the off cell potential of the zinc. So that I have written the formula for to calculate the potential of this zinc electrode or off cell is equal to standard reduction potential of the zinc minus 0.0591 divided by N, log of 1 divided by molar concentration of Zn2 plus, the unit is volt. Okay, now in this formula, what are the quantities which are already we have written in the given data? Standard reduction potential of zinc is there, that is minus 0.763 volt, that you can write here. Yes, that is not a problem. And molar concentration of Zn2 plus is in the denominator, that is given, that is 0.01 molar, that you can write here. And what is not known here? N, that is number of electrons equivalent being transferred during the course of the off cell reaction. So in the standard reduction potential value itself it is given that Zn2 plus. It means that there is involvement of the 2 electron transfer during the course of the cell reaction, so that N is equal to 2 you can take. Now, so you substitute the value of N here as a 2, and now you can start calculating all these values. Log of 1 divided by 0.01 is 2, 0.0591 divided by 2, 2, and this 2 gets cancelled, only 0.0591 is remained. Then that is minus 0.0591. Here minus 0.763 is remained here, and you can add these two, because minus and minus you can add these two, and the final sign is minus itself, so that it is 0.8221 volt is the potential of the zinc electrode dipped in the zinc sulfate solution. Hope you have understood this problem. I will switch over to the second problem. I will read out the second problem. The standard reduction potential of copper 2 plus for copper is 0.34 volt in a solution of copper 2 plus ions with the concentration of 0.01 molar. Estimate the approximate potential at which deposition of copper will occur. This is the same type of problem as in the first problem itself. Here the standard reduction potential of copper 2 plus copper is given as plus 0.34 volt, and in a solution of copper 2 plus ions having a concentration of 0.001 molar. Here standard reduction potential of copper 2 plus where copper is given and molar concentration of the copper 2 plus ion is given. Then you can find out the N value here. What is N? Number of electrons which are being transferred during the course of the off cell reaction. That is copper 2 plus, it is oxidation state of copper is 2 plus, you can take this 2 as the value of N. So N is known, molar concentration of copper 2 plus is known, that is 0.001, and standard reduction potential of the off cell is known, that is 0.34 volt. It means that by using three datas, you can calculate the potential of the off cell, that is copper 2 plus bar copper. Okay, that is what they have asked in this way as estimate the approximate potential at which deposition of copper will occur. It means that you have to calculate the potential of the off cell. Okay, now using the above equation or above formula which you have used in the first problem, the same formula you can use it to calculate the off cell potential. Pause the video and try for the answer. After having done the solution, resume the video. Now you can check the answer. Now, these are the steps involved in the calculation of the off cell potential of the copper, and finally we have got the answer as plus 0.251 volt. If the answer is 0.251 volt, if you obtain, this is the correct answer. Okay. Now I will over to the third problem. A zinc electrode is placed in 0.1 molar solution of zinc sulfate at 298 Kelvin. If the degree of dissociation of salt at this concentration is found to be 0.95, calculate the electrode potential of zinc electrode at 298 Kelvin. The standard reduction potential of zinc is given, that is minus 0.76 volt. Now, this is again calculation of the off cell potential of the zinc dipped in zinc sulfate solution. You have to use this formula as you have used in the first problem itself. Okay, that is the formula you have. In this formula, you have standard reduction potential. It is given in the problem as minus 0.76, that you can substitute here. And value of N is already familiar to you, that is number of electrons equivalent is being transferred is 2, that you can write as 2 here. Log of 1 divided by molar concentration of Zn2 plus. Now the problem comes is, there is a small twist for you. The molar concentration of Zn2 plus is either 0.95 you have to take or 0.1 you have to take. That is the key point you need to understand here. See, when you have taken 0.1 molar solution of zinc sulfate, during the course of the reaction, 0.95 molar concentration of the zinc sulfate is being dissociated, so that the present concentration of the zinc sulfate is not 0.1 molar. The dissociated concentration you have to take, that is 0.95. So therefore that you have to take molar concentration of Zn2 plus is 0.95. Now you can start doing calculation. Minus 0.76 volt minus 0.0591 divided by 2 log of 1 divided by 0.95, that is 0.022. Then you can multiply 0.0591 into 0.022. You will get the answer 0.02955 multiplied by 0.022. You will get the answer 0.00105. You can add these two values. You will get minus 0.7610 volt. The final sign is minus itself. Okay, this is the answer for this question. Okay, yeah, if this statement is being included in the problem, you have to take the concentration of the value of the dissociated concentration. Suppose in the same problem, instead of, if the degree of dissociation of salt at this concentration is found to be 0.95, instead of that, if the dissociation is in terms of percentage, suppose 95% or 90% or 40% is dissociated, means you have to calculate the molar concentration of 40% or 80% or 90% out of 0.1. Say for example, 90% is dissociated if they have given. So what is the concentration of the zinc sulfate solution? 90 divided by 100, that is 90%, into 0.1, that is 0.01. So that you have to include 0.09 concentration if in the problem, if the degree of dissociation is given in terms of percentage. You have to take care of these things. Then the fourth problem is on the EMF of the cell. In this EMF of the cell, so far we have discussed the calculation of the potential of the off cell itself. Zinc is dipped in zinc sulfate solution, or lead is dipped in lead sulfate solution, or copper is dipped in copper sulfate solution, or AG rod is dipped in AgNO3 solution. These are all called as off cell. Now EMF of the cell means it is a complete cell which consists of the combination of the two cell, that is two off cell. Zinc is dipped in zinc sulfate solution and copper is dipped in copper sulfate solution. These two cells are combined through the salt bridge. It will become the Daniell cell. It becomes a complete cell. Now we have to focus on calculation of the EMF of such cells. Now there are two problems which should be discussed on this chapter. Calculate the EMF of the following cell at 25 degrees Celsius. Zinc sulfate bar Zn2 plus, molar concentration of 0.05 molar, double vertical line, that is salt bridge, copper 2 plus 0.25 molar, vertical line, copper. The standard potential of the cell is 1.2 volt. Now straightforwardly they have asked, calculate the EMF of the following cell. This is the cell. This is the cell representation of the particular cell. The potential of this is given, that is 1.2 volt. Okay, now we have to extract the datas. What all datas which are required, or what are the datas given in the problem? Standard potential of the cell, that is 1.2 volt, that they have given. That is standard potential of the cell is 1.2 volt. Then molar concentration of the Zn2 plus is given in the left hand electrode of the cell, that is 0.05 molar. Copper 2 plus concentration is given in the right hand side of the electrode, that is 0.25 molar. Then what is the electrons being involved in this reaction, redox reaction, that is N is equal to 2. Because zinc has to lose 2 electron, copper plus 2 has to get the 2 electron, therefore N value is 2. And what is the EMF of the cell? Then what is the equation you have to use? You have to use the equation which you have been already used in the calculation of the potential of the half cell. Might you have remembered in the derivation, you have derived the Nernst equation for the double cell. The equation is given here. E cell is equal to E naught cell minus 2.303 RT divided by NF log of molar concentration of the C to the power of C, molar concentration of the D to the power of D, and molar concentration of A to the power of A, and molar concentration of B to the power of B for a general reaction we have written here. So the same reaction, the same equation can be written for our electrochemical reaction, that is zinc and copper cells, as in the numerator I have to write Zn2 plus because it is in the product side, and copper 2 plus is in the reactant side. So you have to write molar concentration of Zn2 plus divided by Cu2 plus. This is the suitable equation to calculate EMF of the cell for the present problem is concerned. Okay, now you have to write once again this formula. E cell is equal to E naught cell minus 0.0591 divided by N log of Zn2 plus divided by molar concentration of Cu2 plus. The unit is volt. Okay, what is the concentration of Zn2 plus? It is given here 0.05 molar, that you can write. Molar concentration of Cu2 plus is there, that is 0.25 molar, that you can write here. So N is 2, that is already noted down, that you can write. Standard electrode potential of the cell is 1.2. Okay, after substituting these values, you can calculate this 1.2 you can write minus of 0.0591 divided by 2, that will give you 0.02955. Log of 0.05 divided by 0.25 gives you minus 0.6989. Then you have to multiply this value and this value, that will give minus into minus gives plus. Therefore, multiplication of these two values gives you 0.02065. Then you can add these two, 1.2 plus of 0.02065, that will give you 1.22065 volt. This is the answer for the problem. Okay. The fifth problem is also a same kind of problem, only there is a change in the concentration. Calculate the EMF of the following Daniell cell at 25 degrees Celsius. The cell representation is given, or cell diagram is written. Zn bar Zn2 plus, molar concentration of the is given in the parenthesis 0.001 molar, and salt bridge copper 2 plus, molar concentration of copper 2 plus is given, that is 0.1 molar, and single vertical line copper. The standard potential of the cell is 1.2 volt. Again you can extract the data. E naught of cell is equal to 1.2. Molar concentration of Zn2 plus is 0.001 molar. Molar concentration of copper 2 plus is 0.1 molar. Then what else you require? I think you require N. N is 2. Already you know that. You can write N is equal to 2. With these hints or with these data, you can try for the answer. While trying the answer, you can pause the video and try for the answer. Yes, most of you have tried for the answer, and if your answer is 1.2591 volt, if you have obtained, then it would be a correct answer. These are the data I have written. This is the cell reaction, and this is the formula, and after substitution you will get 1.2591 volt. I hope that you have obtained the correct answer. Then we will move to the next problem. Calculate the EMF of the following cell at 25 degrees Celsius. The cell diagram is given, that is Zn bar ZnSO4 0.05 molar, double vertical line ZnSO4 in parenthesis 0.5 molar, and single vertical line Zn. And this is the only one line problem. Calculate the EMF of the following cell at 25 degrees Celsius. The cell diagram is given here. That cell representation is given. Cell symbol is given. What else we have to get from this cell representation. That is the need of the solution. So you know that you have to use the Nernst equation, of course, for any of the EMF of the cell. You have to calculate the EMF of this cell. Look at this cell. This cell is not similar to the cell representation of the DNA cell. Keenly observe this cell. Zn, vertical line ZnSO4, short bridge ZnSO4, vertical line Zn. It means that on both the side, same electrode and same electrolytes are being present. As in the earlier problems, in the left hand electrode side, we have Zn bar ZnSO4 and copper 2 plus bar copper. But whereas this is not like that, on both the side of the salt bridge, we have same kind of off shell. Then what is the difference then? Then you have to think of concentration cells. What is concentration cell? You know that. There are two types of concentration cell. One is electrode concentration cell and electrolyte concentration cell. Think whether this is an electrode concentration cell. See Zn and Zn. On both the sides, the same electrode, definitely. And the activity of this electrode is same. It is not different. Therefore, it is not an electrode concentration cell. And look at the electrolyte on both the sides. There is ZnSO4 and ZnSO4. Yes, of course, there is a difference in the concentration of the ZnSO4 in the left hand electrode as well as in the right hand electrode. Here 0.05 molar and here 0.5 molar. It means that it should be a electrolyte concentration cell. Yes, now it is an electrolyte concentration cell. Again, the next question comes. Either this is electrolytic concentration cell with the transference or without transference. This is very, very important because the calculation of the EMF of the particular cell is different from one cell to the other cell. That is what you have to rule out all these things. This is electrolyte concentration cell with the transference or without transference. If it is with the transference, the transport number of Zn2 plus should be given. That is not there. So that it is electrolyte concentration cell without transference. So now the thing is now become easier. Now you can use the equation to calculate EMF of the electrolyte concentration cell without transference. That is E without transference is equal to 0.0591 divided by N log of C2 by C1. Now, in this equation, what are the quantities given in the problem? Now, you have to find N. N is equal to 2 definitely because ZnSO4 system having 2 electron transfer. Then, what is C2 and what is C1? Right hand electrode concentration is C2. Left hand electrode concentration is C1. Therefore, C2 divided by C1, C2 is 0.5, C1 is 0.05 molar. That is what I have written the data as here. Now, C1 is also a Zn2 plus concentration, C2 is also a Zn2 plus concentration. So that you should not Zn2 plus and Zn2 plus. Instead, that you have to distinguish the concentration of these two as C1 and C2. Now C2 is known, C1 is known. You have to substitute these values here and log 0.5 divided by 0.05 gives you log 10. Log 10 is equal to 1 and here 0.0591 divided by 2 gives you 0.02955. 0.02955 into 1 is gives you 0.02955 volt. Okay. Mostly the solution of this problem is very, very clear to you. Students, remember, calculate when the problem is asked to calculate the EMF of the cell, you have to be very careful in observing the cell representation or cell diagram. Based upon this, you have to, before going to choose the formula to calculate EMF of the cell. You have to carefully observe what type of cell it is. Either it is a Daniell cell, or it is a concentration cell with or without transference, or electrode concentration cell. That should be very carefully observe and find out. Then after, you have to choose the suitable formula to calculate the EMF of the cell. Okay, fine. Next problem is calculate delta Z naught for the cell reaction Zn, vertical line Zn2 plus, double vertical line Pb2 plus, single vertical line Pb. This is the cell representation, where standard reduction potential of zinc is minus 0.762 volt and standard reduction potential of lead, that is given as minus 0.126. Based on delta Z naught result, will zinc precipitate lead from a solution? There are two things are being asked in this problem. One is calculate delta Z naught. That is the first statement which is being in the problem. And secondly, based upon this delta Z naught result after calculation, they have asked, will zinc precipitate lead from a solution? This is the second question based upon the delta Z naught result. Our first target is you have to calculate delta Z naught, then you have to answer for this second question. Now, how to calculate delta Z naught? When calculate delta Z naught means you can remember the relationship between delta Z naught and equilibrium constant. That is delta Z naught is equal to minus 2.303 RT log Kp. But that is not there here because Kp is not given here. Only standard reaction potential of the two cells are given. So this is not the relationship between delta Z naught and equilibrium constant. So other equation should be delta Z naught calculation. Delta Z naught is equal to minus N E naught F. It means that here N is number of electrons involved in the course of the reaction, and E naught is standard potential of these two cells, and F is Faraday, that is 96,485 coulombs per equivalent. Now, what is the value of N? N I have written here 2 equivalent per mole. What is E naught? E naught should be find out. How to find out? That is given in the step 1. And F, you know that 96,485 coulomb per equivalent. Okay, now in order to calculate this delta Z naught, N should be there, F is there. What is E naught? E naught is given in the step 1 problem. E naught is calculated from the sum of these two reduction potentials. That is, to calculate the EMF of the standard electrode potential of the cell is equal to standard potential of the right hand electrode minus standard potential of the left hand electrode, that is E naught RHE minus E naught LHE. What is RHE here is lead plus 2 bar lead is RHE, Zn bar Zn2 plus is LHE. Now, so wherever RHE is there, I have written here lead minus the potential of the zinc. So standard potential of the lead is given, that is minus 0.126, you can write here, minus standard potential of the zinc you can write, that is minus 0.762 volt. So you can minus into minus becomes plus, and you can subtract minus 0.126 from 7.762, it will give you 0.636 volt. Now the E naught is obtained now. This E naught you can substitute in this equation, that will give you N is 2 minus there, it is there in the equation itself, 2 equivalent per mole into 96,485 coulomb per equivalent into 0.636 volt. It means that every 1 equivalent of the electron transfer, there is an involvement of the 96,485 coulombs. So you can multiply all these numbers and you will get 1,22,728.92 joule per mole. Then what about the unit? This equivalent gets cancelled. Coulomb into volt is remained in the numerator. So coulombs into volt is called as joules, and in the denominator there is a mole, that you can write it as per mole. So the unit is joules per mole. Definitely the free energy, standard free energy unit is in terms of joule per mole, that you can write. You have to convert this into kilojoules. You can divide this by 1000, then you will get minus 122.7 kilojoules per mole. Okay, fine. Now, the eighth problem is also on the calculation of the standard free energy change with relation of the equilibrium constant. I will read the problem. Calculate the standard free energy change for the following reaction at 25 degrees Celsius. Half mole of copper plus half mole of chlorine gas, equilibrium sign is there, half mole of CO2 plus ions plus Cl minus aqueous ions. 1 mole of Cl minus aqueous ions are being discharged. And standard potential of this cell is 1.02 volt. Okay. Then the given values are Kp is given, that is 2 into 10 to the power of 17. It is not 27. Please make a correction. It is 17. R is equal to 8.314 joule per Kelvin per mole. T is equal to, that is temperature, 25 degrees Celsius. That you can convert this into Kelvin. 25 plus 273 is 298 Kelvin. Now, you have to extract the data. You may need the value of N. N is equal to 1. Why? Because half mole of copper reacts with half mole of Cl, means there is only one electron transfer is being involved as per the electrochemical reaction is concerned, that is N is equal to 1. Kp is 2 into 10 to the power of 17, it is not 27, correct it again. E naught of cell is 1.02 volt, that is given in the cell reaction itself. R is equal to 8.314 joule per Kelvin per mole, T is equal to 298. And calculate delta Z naught. This is the, since Kp is given, it should be definitely, it is the relationship between equilibrium constant and delta Z naught. What is the relation? Delta Z naught is equal to minus 2.303 RT log Kp. So 2.303 R is 8.314 joule per Kelvin per mole and T is 298 Kelvin log of 2 into 10 to the power of 17, that is Kp value. Now, log of 2 into 10 to the power of 17 is 17.301. Then you have to multiply all these values. You will get 98,717.05 joules per mole. Why? Because this per Kelvin and this Kelvin gets cancelled. Remaining units are joules per mole only. Now what is the sign? Minus sign is remained. Then you can convert this into kilojoules. You divide this answer by 1000, you will get minus 98.71 kilojoules per mole. This is the answer of standard free energy. Okay. Calculation of pH on the basis of quinihydron electrode. The EMF of the cell using acid solution in quinihydron electrode coupled with calomel electrode was 0.1595 volt. Calculate the pH of the solution. Given standard electrode potential of calomel electrode is given 0.2415 volt. Standard quinihydron electrode potential is given, that is 0.699 volt. By using these data, you have to calculate the pH of the solution. What is the pH equation? When by using quinihydron electrode, this is the equation. pH is equal to 0.4575 minus E divided by 0.0591. Now, since these values are given individually, that is standard electrode potential of quinihydron and calomel electrodes are given individually, and EMF obtained during the measurement of pH is given, that is 0.01595. So that this E is known. Instead of taking this value directly, I can write this value comes out of what? Comes out of standard electrode potential of the quinihydron electrode and calomel electrode. Therefore, I have to put these two values in the bracket and minus E. So this equation I have to write in this way, divided by 0.0591. EQ naught is given, that is 0.699, minus E calomel is given, that is 0.2415. You have to subtract these two values, minus 0.1595 divided by 0.0591. This subtraction of these two numbers gives you 0.455 minus 0.1595 divided by 0.0591. The final answer that you are going to get is 5.0. So pH is measured at this EMF observation is about 5.0. So this is the answer for this question. Okay, next. Last question. A cell is made up of electrode, zinc in zinc sulfate solution and copper in copper sulfate solution of unit molar concentration at 25 degrees Celsius. The standard reduction potential values of zinc and copper electrodes are 0.76 volt and plus 0.34 volt respectively. Given the representation of the cell, that is the first thing, write the electrode reaction, write cell reaction, calculate EMF of the cell. Representation of the cell, zinc is dipped in zinc sulfate and copper is dipped in copper sulfate, that is a Daniell cell. Okay, you have to indicate the physical constants here. It is physical states, it is solid, this is aqueous, this is aqueous, this is solid, that you have to write. Write the electrode reaction. Left hand electrode, zinc is a oxidation of cell, therefore it is taking place at anode. So you have to write the reaction at left hand electrode as zinc has to lose 2 electron, gives Zn2 plus ion. The standard electrode potential of this is this. Right hand electrode, cathodic reaction where reduction is taking place, copper 2 plus ion gets 2 electron from zinc, will give you copper, and standard electrode potential of this cell they have given is plus 0.34 volt. You have to write volt and volt here, that you have to make correction. Write cell reaction. What is cell reaction? But this is the, you have to take the net reaction of this. Zn plus Cu2 plus gives you Zn2 plus Cu, and you have to indicate the physical states of all these species. Then calculate EMF of the cell. You know that E naught of cell is equal to E naught of right minus E naught of left. So right hand electrode potential is, that is copper, plus 0.34 volt, minus of that is potential of the zinc electrode 0.76 volt, then that will give you E naught is equal to plus 1.1 volt. Students, these are the 10 problems I have discussed. One thing I have forgot to explain you, that is in the 7th problem. I did not answer for the this question, that is will zinc precipitate lead from a solution? Yes, based upon the delta Z naught result, delta Z naught is negative value, it is a spontaneous. When delta Z naught is negative for a particular cell reaction, the reaction is said to be spontaneous. Therefore, when zinc and lead cells are being connected with each other, when there is oxidation and reductions are taking place, zinc precipitate lead from a solution. So what is the answer? Will zinc precipitate lead from a solution? Yes, zinc precipitate lead from a solution because it is a spontaneous process based upon the delta Z naught value. Okay, I hope this point is very clear to you. Now, I have discussed all these 10 problems through this lecture. I hope that all type of problems are being clear to you. I also feel that you are little bit more comfortable to solve the problems on this chapter. If it is so, then it would be very nice for the further practice of the problems. You can take up the problems from the physical chemistry textbooks from the electrochemistry chapter. You can try for the different types of questions. With this suggestion, I would like to end up this lecture, and I thank you all for watching this lecture, and thank you for watching once again. Thank you. Have a nice time.